Hello, welcome to the second lecture. In our first lecture, I have told you that how to analyze AC circuit. By analysis of AC circuit means we will be interested to know the steady state currents in the circuit. We will not be interested to know what will be the transient current. Because what happens is this, if supply voltage is varying harmonically, suppose like this here, suppose this is the AC voltage V, with this plus means potential of this point with respect to this I am meaning. Now when I close this switch, I can close this switch here, I can close this switch here, I do not know, or I can close this switch at this point. It is left to chances because supply voltage is already present and it is varying with 50 Hertz frequency. So at any point of time I can close the switch. But what I want to tell is that after that closing of the switch at different instant of time will only change the transient part of the solution. That is the current response. If you completely solve it, as we have seen earlier, it will be some Vmax by Z into sine of omega t minus theta plus another constant into e to the power minus t by tau. The complete solution of this by classical method will be in this fashion. However, if I close the switch here at this point, the equation of this sign, that is t equal to 0, I am measuring from this time. The equation of this waveform then should be written as Vmax sine of this waveform is leading this one by this omega t plus some angle alpha. That is, if alpha equal to 0, as if I am closing the switch at this point when voltage is 0 going up. If alpha is equal to pi by 2, it means that I have closed the switch when the voltage is maximum. So this alpha, have you understood? It has nothing to do with power factor angle of the circuit. Are you getting? That is what, in which way should I write down the input voltage equation? So this alpha is decided by the switching instant. Decided by switching instant. Anyway, I will not go into very much detail of it, but physically tell you how to find out the total response of the circuit if you consider different instant of switching. For that, we should remember only two facts. That is, in case of a purely inductive circuit or inductance, current through inductor cannot change instantaneously. That is one of the very basic fact. Current through inductor cannot change instantaneously. And also for a capacitor, voltage across its plate, the plate of a capacitor cannot change instantaneously. Voltage across the plates of a capacitor cannot change instantaneously. Of course, the more fundamental rule is that the flux linkage through an inductor cannot change instantaneously. From that, we can show that current through the inductor cannot change instantaneously. Now, how this will help us to draw the exact waveform of the current without doing any mathematics, that I want to tell you. That is very interesting with reference to the same circuit. Now, suppose this is the supply voltage which is existing across the supply voltage terminal. Like this. Let us consider a current a circuit, inductive circuit, where the current response will be lagging the voltage in the steady state. Steady state current response is like this. This is current, steady state current, steady state, and this is the voltage, and this is the time axis, omega t. Now, what I am telling, that the circuit, the switch may be closed, this switch may be closed when the voltage is 0 going towards positive, or I may close the switch at this point of time when voltage is maximum, or I may close the switch at this point when 0 but going towards negative, like that. Now let us consider what will happen to the current response. And what is ISS? ISS is the steady state current, which we can get by the phasor diagram. This current is present, steady state current. Now suppose, let us assume I am the luck so favors that I have closed this supply voltage, the switch of the circuit, when the supply voltage was this much. Are you getting? Supply voltage, two terminals are there, voltage is changing with time. Now suppose it has so happened, I have closed the switch without knowing, of course, that it has so happened when the steady state current is 0, at that time the supply voltage has been switched on to the circuit. Steady state demands the current through the inductor at that instant is 0. And prior to the switching on of this circuit, what was the current through the inductor? It was 0. That let us assume inductor was not carrying any current prior to this switching action. Therefore, by this fact that current through the inductor cannot change instantaneously, the moment you close the switch, prior to that instant, current through the inductor was 0. And when you close the switch, current through the inductor, because of steady state current, will be also 0. Therefore, if someone closes this switch at this instant, there will be no transient response. Circuit will straight away go to the steady state condition like this. This point will be further clear if I consider the closing of the switch at some other instant. For example, if somebody closes the switch such that voltage was 0 and rising at this point, suppose you close the switch, then let us see what happens. If the circuit is closed at this point when voltage was 0 but going towards positive, then your steady state demands current should be of this magnitude flowing in the opposite direction, because I direction I have assumed like this. But prior to the switching on here, what was the current through the inductor? 0. And if you close the switch here, the current demanded by the steady state solution is this much, negative. But then this rule will be violated. Current through the inductor cannot change instantaneously. So what appears in the circuit on its own, that another current of equal magnitude here, this one, will appear here. In order to satisfy that condition, current through the inductor cannot change instantaneously. Of course, one should not be under the impression where from you are bringing the current. The fact is this, you forget about physical aspects. You solve the circuits. You will see yourself that this current appears in the solution in the form of this exponential term. So what will happen? This current will appear. I am trying to giving you a physical interpretation of that solution. What is this? That is this current, this length you cut out here. This much current has to flow at this point of time in the opposite direction, such that this condition will be satisfied. However, there is no voltage to sustain this current. AC current will be sustained by this one. Okay. So this current will decay down with its own time constant decided by L by R ratio of the circuit. Therefore, this one, the total response of the circuit will be here if I plot it, the current waveform, it will start from 0. Initially, for some 1.5 cycles or 2 cycles, this current response will be somewhat asymmetrical. After few cycles, it will be fully sinusoidal, because by that time this exponentially decaying component has decayed down to 0, or practically no significant current flows because of that exponential thing, and your final steady state will be reached, and that value is decided by L by R of the circuit. So this aspect, of course, I will ask you, because you have done also a network course earlier, to solve this circuit, keeping this alpha in the circuit, where alpha will take care of this instant. You can write down a program that alpha is this much, then what will be the current response, and that you can plot using MATLAB or whatever it is, the current response of the circuit, and see the asymmetry introduced in the circuit at this instant. But the most important point is, there are some instants when the circuit is switched on, there will be no transient present in the circuit. Circuit will straight away go to the steady state condition. Anyway, this has got some far-reaching implications in some circuitry. For example, I will tell you one just example in the circuit. Suppose you have a circuit whose R value is very low. R is low. Inductance value is large. Such that the current in the circuit will be practically lagging, steady state current in the circuit will be practically lagging the voltage by 90 degree. Suppose this is the voltage. This is suppose the voltage. And the current response in the circuit will be practically lagging 90 degree. Okay. So this is voltage and this is current. It will be somewhat like this. So this will be the current waveform in the circuit. Steady state current. Obviously, if the circuit is closed at this point, what will be the current response? It will be I max by omega L, because R is suppose negligibly small, into sine of omega t minus 90 degree, like that, whatever current, and circuit will go straight away to steady state condition. But situation will be somewhat different if the circuit is closed at this point. This is time axis, omega t. If you close the circuit at this point, omega t equal to 0, how much is the steady state current? Negative this much. Do you think only this current can exist in the circuit at that point of time? No, because inductor current cannot change instantaneously. So there has to appear a current whose length will be this equal to this here, you cut down. And this current, there is no voltage to support this current. This current will decay with the time constant of the circuit, L by R. Now, here in this circuit, I have assumed R to be very low. So, this current will fall rather slowly here, like this. So, in the circuit, what will be the total current? Point by point addition of this current and this current will be the total response of the current in the circuit. Now, note these instants. What will be the total current in the circuit? Practically twice I max. Because R being very low, it has not gone to 0 even in the next peak here. In the next cycle, this may persist also, if not twice, but substantially large current will be existing in the circuit. So what I mean to say, there are some situations, and particularly with circuits, where current magnitude may be practically double, and this is called doubling effect, and which are relevant in power system analysis for rating, for deciding the rating of the circuit breaker, etc. But let us not go into those power system aspects, but I just want to point out one should have a fair idea of what he is doing with a circuit when he closes the switch. And also this thing happens when you switch on a very inductive load from an AC source. If you are lucky that you have closed the switch here, there will be no doubling effect. Circuit will straight away go to the steady state condition. But if you are a unlucky fellow, I mean, it may so happen that you have closed the switch here, right at that point. Then doubling effect will take place. And in case of transformer experiments, you will often find with secondary open circuited, primary is a huge inductance. If you switch on from an AC supply, sometimes fuse blows, although secondary is opened. It should draw a very low current. But because of that is called magnetic inrush of current, one of the factors of this high current will be this one. It depends upon the instant of switching. Sometimes fuse blows, sometimes does not blow, because one really does not know when he is switching on the circuit. Yes, please. Doubling effect is see when you solve any AC circuit here, IT, forget about the physical interpretation. Suppose I assume when I close the switch at any point of time, I am going slowly, but listen carefully once again. Suppose applied voltage could be anywhere in this waveform. I do not know when I am closing the switch. Suppose I close this switch here. What should be the equation of the voltage? V max sin omega t, I will write applied voltage equation. If I close the switch at this point and voltage is rising, what should be the equation of the voltage? V max sin omega t. It is sine function. Suppose I close the switch at this point when the voltage is maximum. What should be the equation of the sine wave now? I have started counting time from this instant. What will be the equation of this one? That is cosine omega t or sine omega t minus 90 degree, because then see your supply voltage is omnipresent across these two terminals. Now by which equation you call it is solely my own business. Now suppose I have closed the switch here. I will write this equation because I have started counting my time from this instant. The equation of this waveform will be what? V max sin omega t. Now suppose I close the switch here. Suppose at this point switch is closed. Then this equation, this one, omega t equal to 0. Had there been a waveform here starting, this would have been my sine wave. So this is leading this by 90 degree. So this is cosine omega t. Are you getting? The equation of the voltage will be this way. Therefore, in general, if you close the switch at any point of time, what will be the expression of the voltage? It will be V max sin omega t plus alpha. This alpha, I am trying to tell, has nothing to do with your L omega r, not a property of the circuit, but rather the instant when I am closing the switch. Now, by imagining that alpha equal to 0 means I am trying to tell I have closed the switch at the instant when voltage passes through 0 and increases. If alpha equal to 90 degree, I am trying to tell I have closed the switch when voltage is maximum, like that. Okay. So with this voltage in present as a general case, where alpha could be anything between 0 to 2 pi, you really do not know. One can do a little bit of research, what I am trying to tell. This is the voltage and I want to find out the current. So I will write down Ri plus L di dt. And I will solve this expression assuming alpha to be constant now. Once I have closed the switch, alpha is known. I will calculate the current. Now tell me what will be the, by classical way, let us do first order differential equation. Of course, the forcing function is a function of time. but you know several ways of solving this Laplace transform, this, that. Now, what will be the response of the current? The response of the current will be this one, V max by root over R square plus omega square L square will be there, sine of, this will be omega t plus alpha minus theta, where theta is tan inverse omega L by R. And then I am telling this will be another transient portion will come. Okay, another transient portion will come. It will have a magnitude, and this term will be like this, where tau is L by R. Tau is equal to, tau equal to L by R. This tau is L by R. Now, you will see after solving this I leave as an exercise. You solve it by classical method. After solving this, you will find at omega t equal to 0, what is this current? B max by this sine of alpha minus theta. You will find this term is also, minus B max by Z sine of alpha minus theta will automatically come. To satisfy the condition at t equal to 0, current has to be 0. Now, therefore, if you now solve this circuit by considering alpha equal to 30 degree, alpha equal to, any interval change you do and find out the current response, you will find the response of the current will be sometimes asymmetrical and finally coming to steady state, and sometimes it will be going straight away to steady state. For example, this term, the magnitude of this term, I can straight away write. It will be by inspection I am writing, not doing any mathematics, but knowing this one. This will be this V max by Z, into sine of alpha minus theta, preceded by a negative sign it will come. So, at what time this term will not be present? No transient will be present at what time? When alpha equal to theta. This response I will be B max by Z sine of omega t plus alpha minus theta minus of B max by Z into sine of alpha minus theta will come if you solve it, and it will be e to the power minus t by tau. When this exponential term will not be present? When alpha equal to theta. Suppose I don't bother about any physical interpretation. You solve it classically. You will get a solution like this. What is alpha? Alpha is my own interpretation. That is when I am closing the switch. Let us assume I have closed the switch at omega. I will not say omega t, I will say at the time when voltage is 0 going to positive, or alpha will be equal to 90 degree if you have closed the switch at this instant, like this. If you have closed the switch at this instant, I will say alpha equal to pi and so on. Clear? So, this way we will be doing. So, anyway, this will be the transient response of the circuit. Now, you go through it. Okay. Now, this is okay. But what I will do is this now. Let us forget about this transient aspect right now. We will be interested in steady state performance of AC circuit. So, we will assume that the transient have died down after some time and only sinusoidal voltage and currents are existing. Now, with that in mind, let us now come to the power in an AC circuit. Very quickly I will go. Power in AC circuit. Power in AC circuit. While dealing with power in AC circuit, the problem is that there are some times when the power will be drawn from the supply and sometimes power will be given back to the supply. So, what we calculate is the average power drawn from the supply, and steady state has reached, and the expression of the power you know it will be V into I into cosine theta, where V is the RMS value of the voltage, I is the RMS current, and theta is the power factor angle. This is the, and we give a name kilowatt. The primary thing what I want to tell here, apart from this, there are quantities which are called VI, whose rating is kVA, and another quantity called Q, which is called reactive power, which is VI sin theta. And it is written like this. Remember, cosine theta, sin theta has got no dimension. So all of them, it appears, should have same units. Kilowatt, kVA, kVAR are given different names to each of them in order to distinguish several things. The idea is like this. Suppose you have an AC circuit where a pure, so this is called active power, this is called reactive power, and this is called volt ampere rating of the circuit. Now I will tell you what each of these means. That I will tell you in the form of an example. Suppose you have an AC supply 200 volt RMS applied across a 20 ohm resistance. You have another circuit where same 200 volt AC I have applied, and it is purely inductive, and whose resistance or impedance is 20 ohm, reactance is 20 ohm. And you have another circuit here which is capacitive and which is also 20 ohm reactance, 1 by omega c, and this is also 200 volt. Now if you connect 3 ammeters here in the line of each of the circuit, each of them will read 10 ampere. Because MI meters reads the RMS current, each of them will read 10 ampere. This problem I will pose it in this way. Suppose there are 3 consumers. Consumer 1 has connected a 20 ohm purely resistive load across the supply given to his house, 200 volt. Another consumer has connected a purely inductive load, 20 ohm. And another consumer has connected 20 ohm purely. Now in inductor, if you draw the voltage and current waveform, you will find sometimes inductor is absorbing power from the circuit. That we can easily identify. If you draw this one, this is suppose the voltage waveform of the inductor, and this is the current waveform of the inductor, like this. At this point, voltage and current directions are opposite, and it will deliver power. At this point, so long voltage and current are positive, it will absorb power. Okay? Any element, suppose you have an element, this point should be understood. If you have any element, resistance, inductance, capacitance, whatever it is, if the voltage polarity across the element is like this and current enters through the plus terminals, it absorbs power. Any device which has got this side plus, this side minus voltage, and current comes out from the positive terminal, it delivers power outside. This we know from a battery concept and this one. In case of a inductive circuit, therefore, sometimes power will be drawn, you can identify those zones, and sometimes power will be given back to the supply. And this inductor, if you touch, it will never be hot. Sometimes it stores energy, sometimes it pumps back energy into the source. So a to and fro motion of energy takes place in an inductor and also in a capacitor, because they are energy storing devices. However, in a resistance it is not so, because of the fact the voltage and current relationship in a resistance is like this. This is the voltage, this is the current. When the supply voltage polarity changes, current too changes. Therefore, power is always absorbed by a resistance and it is never returned back to the supply. But in case of inductor, it is not like that. For example, consider this zone. This zone. Inductor is like this. This is the voltage I have plotted, inductor, VL, and this is the current direction I have assumed, from which I have got this solution. Now, between 0 to pi by 2, you find voltage is really positive. So, this is plus, this is minus. But what happens to current? Current I have shown here, but got negative. Actually, current is flowing like this. Therefore, from the inductor, from the positive terminal, current is coming out. So, it acts as a battery sort of thing. It gives out power. Consider this instant. Consider this instant. When voltage across the inductance is really positive, that is whatever I have assumed here, that is correct, and current is also positive, it absorbs power. So, over a cycle 360 degree, sometimes it draws power from the supply and the same power will be returned back at different time zones, that we can easily find out. The point is, this will not be hot. This resistance you touch, it will be hot physically. It is absorbing energy and dissipating it, and there is no question of any recovery because of this nature of current. In a capacitor too, it will store energy some cycle, and in some other cycle it will give back energy. Now, the point is, suppose you are supply authority who is giving supply to different consumers. Now, which consumer will be more acceptable to you? This fellow, or this fellow? Which one? First one. Because of the fact, here at the entrance of the consumer's place, energy meter will be placed. And energy meter is nothing but watt meter, and then you multiply with time like that. So, basically its reading will be VI cosine theta. So, at the end of the month, the energy meter reading of this fellow will be 0. Energy meter reading of this fellow will be also 0. But energy meter reading of this consumer will be quite high. Are you getting? Cosine theta of this power factor here is 0. Power factor of this fellow is also 0. But power factor here is unity. Therefore, this, although they have connected inductor, the consumer can tell always, I have not used your energy at all. Okay, I have taken some time, but given you back next time, in the next cycle, next half cycle, or so on. So far so good. I mean, it appears okay, logical. But there is a problem. Problem is that you see your supply authority. Now, before I go to that, so this circuit, what is the volt ampere rating of this circuit? Is 200 into 10, that is 2 kVA. Volt ampere rating of this circuit also I will tell 2 kVA. This is also I will tell 2 kVA. Okay, all the consumers are rated to be 2 kVA. But the problem which comes for the supply people is like this, that see, all the consumers are connected in parallel, na? All the consumers are connected in parallel, and supply authority is giving you power through cables or overhead lines, starting from your generating stations right up to your doorsteps. The cable is coming at various points. The consumers are connected in parallel. So, the total current in the circuit will be the sum of all these currents. Clear? The magnitude of the current to be delivered by your generator or your overhead lines will be decided by some of the currents. How much current your overhead conductor will carry is not decided by how much kilowatt one is consuming. It depends upon the amperage, how much ampere you are taking. Therefore, the size of the conductors will be larger. That is, if your consumers are like this, all have connected inductive load, let us assume 20 ohm each one will carry 10 ampere. So 30 ampere has to be carried by these conductors, which is connected between generating station and these fellows. And the conductor cross section will be higher. So supply authority has to invest a lot at the initial stage, with the understanding all of them will carry some 10 ampere current. So conductor cross section, and also, as you know, these conductors has got some resistance, the transmission lines, there will be power losses in the lines. Although your consumers is not using any active power here for this inductive and capacitive load, but they are contributing to the total magnitude of the current, which is to be supplied over transmission lines, which may have resistance in them, and therefore there will be unnecessary power loss in the transmission lines. So supply authority has every point to tell, okay, you are not using any power, that is true, but to give you that much of power to play this game, that is, you take power, give me power, I have to spend lot of power in the transmission line. Who will pay for it? Is it clear? Therefore, what power supply authority, to avoid such imaginary consumers at any length, they will specify you have to take power at so much of power factor, otherwise you will be penalized. So sometimes power system authority calculate the real power, how much kilowatt he is drawing, and also he will calculate how much kVAR, reactive power he is drawing, and then he will be billed. In fact, for big industries they do like that any industry drawing power say at 0.3 power factor, they will be highly penalized for their reactive power. Okay, so in AC circuit these things must be understood. So you calculate the active power, reactive power, and see like that. But in practice what happens is this so the ideal situation would be all the load is having unity power factor, so far as the supply point of view, but unfortunately that cannot be met because of the load inherently is inductive in nature. For example, your fans in your house, they are inductive. Transformers connected in the power systems, they are inductive. The fluorescent lamp is having a choke in the circuit, they are inductive. So there will be power factor, existing power factors, which is dictated by the existing loads, for which consumer should not be blamed. That is having a lagging power factor in general. Induction motors, they are all lagging power factor, largely used. So generally that's why they will specify, see, power factor you have to do, maintain something like 0.8 power factor, like that is a very standard practice. Now suppose I will just tell you one thing and then go to my next topic, that is, suppose you have, your hands are tied, in your house you have connected a pump which is inductive in nature, and suppose its power factor is 0.6,